Well, good morning there, students. It's time for some chemistry, right? Hey, I'm trying new things all the time, and look at this. It looks like we have sunrise coming up over Europe. Wow, pretty cool. So, all right, where are we at? Um, you should have read an assignment yesterday on ionic bonding, and I'm going to go through a video of notes on ionic bonding today. So just, I know it's maybe a little bit out of order. I maybe should have had the video yesterday for you. I didn't, so there we are. So I, of course, want you to take notes on the video, and then I'm going to be giving you some answers to the book questions that you've had over the last 2 days for you to check yourself. And not much an additional assignment today, other than I have another little video clip that I want you to watch in preparation for tomorrow. I'm hoping to have a special treat for you tomorrow. Excuse me. So I hope to have a special treat for you tomorrow, and I'd like you to watch a little video clip just in preparation. So let's get on with today's lesson. Hopefully I can share my screen here. Okay. Oh, cool. I didn't know I could do that. I still have me in the corner with, you know, the sunrise over Europe. So it's Wednesday, April 15th. It's amazing how, you know, I was fine all morning and I start this video and now I got a cough. Wow. I think Murphy's got some laws about that. Here's our learning targets for today. I can define ionic bonding. I can determine the formula of simple ionic compounds. I can identify common properties of ionic compounds. So here we go. All right. So just a note, the word bonding refers to attractions that hold particles together. And we have different types of chemical bonding. All right. We're starting out with ionic, which I think is the easiest for students to understand. In this chapter, we're also going to talk about metallic bonding. And in the next chapter, we're going to talk about covalent bonding. Okay, and it's just different ways that atoms are attracted and hold together to each other. So ionic bonding, when we use that word, ionic bonding, we're referring to attractions between ions. So if you really want to get a specific definition for ionic bond, it has to be the electrostatic attraction between ions. All right, electrostatic. I'm throwing around some big words here. You are familiar with electrostatics in some sense, okay? At some point in time as a kid, maybe you rubbed a balloon on your head, and, you know, once you rub the balloon on your head, I can't do this very well because I don't really have much hair, but if you had hair, you know, you see that the hair sticks to the balloon then, or you can rub the balloon on your head and then you can stick the balloon on the wall. That's because of the charged particles, and there's attractions between the charged particles. So electrostatic is just that attraction between oppositely charged particles, okay? There's an electrostatic attraction between ions. That is what makes an ionic bond. So two things have to happen. First, we have to have a transfer of electrons to form the ions in the first place. And that was what section 7.1 talked about, the formation of ions. Positive ions are cations, negative ions are anions. Then the ions themselves will be held together by those attractions. So once we form the ions, then the positives and negatives cling to each other. So, simple example. It's kind of a crude drawing, but here's a sodium atom, and it's got 11 protons in its nucleus, and it's got 11 electrons. 2 in the first energy level, second energy level has S and P full for 8 electrons, and then there's 1 electron in that outermost energy level, so 1 valence electron. Here's an atom of chlorine. It's got 17 protons in its nucleus and 17 electrons, 2 in the first energy level, 8 in the second energy level, and it's got 7 in the third energy level. So we've got 7 valence electrons. So what's going to happen? Well, sodium, we talked about in the last chapter, sodium as an alkali metal tends to lose this electron rather easily. It's just not holding on to it. It's got a low ionization energy. Chlorine really likes electrons. It wants to gain an electron. It's got a high electron affinity or electronegativity. So if these two atoms, just through normal course of interaction, happen to get close together, chlorine takes away, oops, it's not supposed to be the whole electron here. Let's see, somewhere, there it is. Here's my representation of, all right, chlorine grabs that electron, takes it away from sodium, and that electron comes over here. Now look, chlorine has 8 valence electrons now, effectively. Oh, it's filled up its noble gas configuration. Sodium, by emptying that energy level, also has a noble gas configuration. But sodium has 1 less electron than it started, so now there's an excess of positive on this. So the sodium becomes a sodium ion, Na+. Chlorine has an extra electron, so it becomes a chloride ion. Remember that the negative ions change their name to end in IDE. So chlorine becomes chloride. And the two of these together would be called sodium chloride. You've heard of that. Here you've got an explosive, highly reactive metal. Here you've got a poisonous gas. But if you put them together and they trade this 1 electron and stick together, you get a compound that's really tasty on your French fries. Talk about the amazing world of chemistry. Now, atoms are rarely by themselves. If I had a piece of sodium and a sample of chlorine gas, there would be millions, billions, trillions of atoms in those samples. And so you got to picture all of those sodiums losing electrons to all of those chlorides. And we form all these ions. Now, ions are not picky. You know, this sodium ion right here, as a positive charge, electrostatic attraction occurs between all opposite charges. So this sodium is attracted to all the chlorides. It want to be surrounded by chlorides. And this chloride ion, the negative ion here, is attracted to all the positives. It wants to be surrounded by the positives. And so what happens is the ions fit together in some sort of structure that best allows the as close a contact as possible between opposite charges, but remember, sodium ions don't like each other. Okay, now, if you just imagine these things, in this case, forming kind of a squarish pattern, and if I just kind of magnify this part right here and look, you know, here's 2 sodiums and here's 2 chlorides. And look at the distances. The distance between the items on the corners here, this chloride and this sodium, that's a shorter distance than if you look diagonally, right? So the 2 positives are a little further apart, and the positive and negative are a little closer together. The 2 negatives are a little further apart, but the positive and negative are closer together. And so this is just an example of how the ions are going to try to fit together to maximize the attractions and minimize the repulsions. Now, some other factors come into play, as in how big are the ions? Not all ions are going to have charge of just a single unit. You know, the sodium is just a single positive and chloride is just a single negative. We're going to get other things, but they're going to form into some sort of pattern. So here's an example. You know, what if you had your positive ions were +2s and your negative ions were -1s. And so I don't know if this is right, but I just tried to draw a pattern where every positive was surrounded by negatives and every negative was surrounded by positives, but try to keep the positives apart from each other and the negatives apart from each other. And the overall compound still has to be neutral. Let's get that in here right now. The overall compound is still neutral because for every electron that was lost, somebody gained an electron. The total number of electrons is still the same. The net charge on an ionic compound is always 0. I'll try to come back to that in a little bit. Hey, this orderly pattern that forms, this has a name. It's called the crystal lattice. Okay? A crystal lattice or crystalline structure is the orderly repeating arrangement of particles in a solid. Not all solids are crystalline, although some people go with the philosophy that only true solids are crystalline. Orderly repeating arrangement of particles. If the particles have this orderly pattern, it's a crystalline solid. Okay, let's just try another example here. All right, so here's a calcium atom. And if you look at the outermost level, it's got 2 valence electrons. Here's a sulfur atom, and in the outermost level, it's got 1, 2, 3, 4, 5, 6 valence electrons. Okay, well, sulfur has a rather high attraction for electrons. Calcium has a rather weak attraction for electrons. So if they come together, sulfur says, come here, little electron. But that's not enough, right? You know, neither calcium or sulfur would be happy yet. Sulfur's up to 7. Calcium's got 1. So they'd be much happier if there's a transfer of 2 electrons. Well, that's going to leave the calcium short by 2 electrons. So it's now a calcium 2+ ion. And sulfur, remember, changes its name to sulfide. And we'd have a sulfide 2- ion. So when we're dealing with ions, and I talk about the charge, you have to have a magnitude with it, okay? If you only put a plus sign or a minus sign, that implies that it's a charge of 1. If it's anything other than 1, you either need to go with 2 pluses or 2 minuses, or you put the number 2 in front of it. All right, so let's get to the idea of a formula unit. If I asked you what the formula was for water, I'm pretty sure every one of you, I hope, would say H2O. That represents a molecule of water, and molecules are going to be in the next chapter. In a molecule, that is the actual distinct unit of atoms that are bonded to each other. So in a water molecule, 2 hydrogens are attached to 1 oxygen, and that's it. If you look at an ionic compound, it's more than that. All the ions are attracted to each other. And so there is no real molecule. So we write the formula in a different way. What we do is we say, what's the lowest ratio? So if I were looking at magnesium and fluorine, magnesium has 2 valence electrons. Each fluorine has 7. So if magnesium transferred 1 electron to a fluorine, the fluorine would have 8. It doesn't want any more. So we need another fluorine to come along. That second magnesium electron could go to the second one. And so in order to make everybody happy, we need a ratio of 1 magnesium for every 2 fluorides. That ratio is what we write down when we're writing the chemical formula for magnesium fluoride. And that ratio is called a formula unit. It's the lowest ratio of the ions in the compound. So we use this kind of in place as sort of a fake molecule. We think of this as the unit, but we have to, in the back of our minds, remember that really all of these ions are attracted together. If you have a crystal of an ionic compound, essentially the entire crystal is bonded together. I suppose from that standpoint, you could call the whole thing a molecule. The word molecule doesn't apply very well to ionic compounds. So we have a different name. We call it a formula unit. Now, what's the charge on the formula unit? Well, magnesium was a 2+, and each fluoride is a single minus, but the ratio is 2 to 1. So the ratio charge, we got 2+, single minus, that adds up to 0. The compounds overall are still neutral. The net charge is 0. Continuing. All right, I got aluminum and chlorine. What's going to happen here? Well, each chlorine has 7 valence electrons. Aluminum has 3 valence electrons. Aluminum would like to get rid of those electrons. Chlorine would like to gain electrons. Okay, so if chlorine takes an electron away from aluminum, oh, now that chlorine's got 8 valence electrons, it's gained 1, so it is now a chloride, single negative ion. But aluminum's got 2 more electrons. It doesn't want those. So maybe there's another chlorine in the neighborhood, and aluminum could lose another electron. Now that chlorine's got all it wants. It's a chloride ion. Aluminum still got a 3rd electron, so it would have to go to yet another chlorine to form a 3rd chloride ion. And overall, aluminum has lost 3 electrons, so it's got a charge of 3+. I think I told you the other day that sometimes I fall into a bad habit of putting the number after the charge. The correct way to do this is to have the number in front of the charge, and I didn't catch that before I made my video. I'm sorry. How would we write the overall formula? Well, the ratio of aluminum to chlorides is 1 to 3. The ratio is just the opposite, basically, of what the charges are. So AlCl3 is the formula for aluminum chloride, and we call that one formula unit. So let's do a couple more examples. Let's think about strontium here. Strontium would have, let's see, two valence electrons. Bromine would have 7 valence electrons. So if we're putting strontium and bromine together, well, bromine could grab one of those electrons, but then what happens next? Well, we don't have situations of just individual atoms typically. So next, we'd have another bromine. In trying to do this, I bought myself a new laptop for at home, and it has a touch screen. So I'm learning how to try to manipulate some things here. So this bromine had 7 electrons. I'm finding out that my aim with my stylus is, well, that's interesting. If I hold my stylus up to my background, it disappears. I got to hold it in front of my face. Apparently, the computer recognizes anything that's not a person and puts the background on it. That's interesting. Sorry. I'm getting fascinated by the technology. All right, that bromine is going to grab this other electron. And so we're going to end up with a strontium 2+ and a bromide single minus and a bromide single minus. And so our formula is SrBr2. Hope that makes sense. Okay. Right now, I'd like you to pause the video and try to work out what would be the formula between rubidium and sulfur, and resume when you've done that. I'm assuming that you just did that, and so I'm going to work it out now. We got rubidium with 1 electron. Sulfur has 6 valence electrons. So if sulfur took 1, sulfur's not happy, but rubidium doesn't have any more. So we need another rubidium. I wanted it to have blue. Don't know why that changed. Okay, so now sulfur grabs the electron from the other rubidium, and we see that we have a rubidium plus, another rubidium plus, and a sulfur 2 minus. The sulfur's gained 2 electrons. Now, it's quite common for students to get a little bit confused about the charge of the ions, because what's being gained or lost is electrons. And we associate gaining as positive and losing as negative from our background. That makes sense. But in this case, you have to remember what is being gained and lost. The thing being gained is negative charges. So sulfur, when it gains electrons, becomes more negative. So you're gaining a minus. In this case, it's gaining 2 minuses. When you go back and draw the overall particle, remember, the nucleus still only has 16 protons for sulfur, but now it's got 18 electrons around it. So it's got an excess of negative. So we're gaining a negative, forming negative ions. We're losing a negative to form positive ions. Our formula in this compound would be Rb2s. Great. I'd like you to pause the video and work out a formula for sodium nitride. And here's assuming that you did that. Wonderful. I'm going to go through and say sodium's got 1 electron. Nitrogen has 5 electrons. So it's going to take 3 sodiums to pair up with the 1 nitrogen. Okay, we can have this electron, this electron, this electron, and that means each sodium is going to end up with a single plus, and the nitrogen is going to end up with a 3 minus, and our formula would be Na3N, sodium nitride. One more. Please pause the video and work out aluminum oxide. Welcome back. Aluminum has 3 valence electrons. Oxygen has 6 valence electrons. So if we start pairing these up and say, well, oxygen takes away that electron, and oxygen takes away that electron. Now the oxygen's full, can't take any more, but aluminum still got 1. So what do we do? Well, the atoms are not there by themselves, so let's imagine there's another oxygen around. It also had 6 electrons. So it could take that last electron from this aluminum. Okay, now the aluminum has emptied out its outer shell. That's good for aluminum, but this oxygen isn't happy yet. So you know what? There's probably another aluminum atom around. and it's got 3 valence electrons. So this oxygen could, apparently, I had to group there. All right, this oxygen could take that electron. Now this oxygen's happy, but this aluminum still has 2 electrons. So what do we do next? Well, what if there's another oxygen in the neighborhood with its 6 electrons? It could take electron from aluminum and another electron from aluminum. And I think we got there, right? We have aluminum, that's a 3 plus, and another 3 plus. And then we've got oxides, which are 2 minus, 2 minus, 2 minus. And our overall formula represents the lowest ratio, Al2O3. Now, if you haven't picked up on this, the numbers that I'm writing in, I find myself pointing to my screen with my stylus, and you can't see that. Oh, okay. The numbers on here, they're called subscripts. They're written a little bit below the line. The subscript always refers to the symbol right in front of it. Okay, so 2 aluminum, 3 oxygen, or in this case, it's ionic compounds, so it'd be oxides, aluminum oxide. All right. So one more thing here today. We're going to go through properties of ionic compounds. So ionic compounds are usually crystalline solids at room temperature. And that goes along with the second point, is that they have high melting and boiling points. Okay, so if it takes a lot of heat before they melt, and even more before they boil, well, that means at room temperature, which we consider relatively low heat, they're going to be solid. They're not melted yet. Okay, there's a reason for that. When you think back to that crystal lattice and all those ions are attracted to each other, those are very strong attractions. So in order to go into a liquid state, the particles have to kind of break some of the attractions from each other to be able to move around. Well, if we have strong attractions, it's going to take a lot of energy to get them there. Okay, so ionic compounds, high melting and boiling points, solids at room temperature. This is not a very clear-cut property, but some ionic compounds are soluble in water. That, you know, if it's soluble in water, you can't say it's definitely ionic or definitely covalent or anything like that. But I wanted to try to explain what's going on. Here's a picture of a water molecule from the next chapter. Okay, you know it's H2O and it's covalent. They're going to be sharing electrons. But what I want to point out on this molecule is, see these dots here that are representing electrons? This side of a water molecule is very negative. And it turns out this side of the water molecule is kind of positive. And so a water molecule has a positive and negative end. And so those ends are going to be attracted to the positive and negative ions. And what can happen is water molecules, when you put an ionic compound in water, the water molecules surround the ions, and eventually, if there's enough water molecules with enough attraction, they pull the ion away from the other ions. It's kind of a tug of war. If the ions are more attracted to each other than to the water, it won't dissolve. If the ions end up being more attracted to the water molecules than each other, it will dissolve. So sodium chloride, dissolves in water. Now I'm trying to think of a compound that doesn't. And I'm trying to keep it to compounds that we'd be somewhat familiar with. Sodium sulfide, I would suspect, doesn't dissolve very well in water. Yeah, we can move past that. Now, if you dissolve the ionic compound in water. Well, then the solution has ions. It has charged particles that are able to move around in the solution, and that can conduct electricity. In order to conduct electricity, you have to have moving charges. So in a solid state, ionic compounds do not conduct. But if they're dissolved in water where the charges can move, it will conduct. Or if you melt an ionic compound into a liquid, now the charges can move, it will conduct. So molten sodium chloride will conduct electricity. Solid sodium chloride, no. In the solid state, ionic compounds tend to be brittle. So I have, I believe on the next slide, a little diagram of that. So here's my crystal lattice, and you got these ions that are all lined up with each other, really nice, right? Every positive is attracted to negative, every negative is attracted to positive. The positives are trying to stay apart from each other, negatives are trying to stay apart from each other. And what if we take a hammer and we come down and we whack this compound? And when I do that, I apply a force and I move some of the ions. Well, notice what happened here is when I moved them out of place, these negatives started getting closer together than they would like to be. And these positives got closer together. And these negatives got closer together. These positives got closer together. In the ionic crystal lattice, you can imagine that the ions are in their best possible positions to maximize attractions and minimize repulsions. So if you move those ions from those positions, you're going to start creating repulsions. So when we hit this and we push some of these ions out of place, well, now you create repulsion and this piece breaks off. Oh, so if you take an ionic compound, if you took a big piece of rock salt, and if we were in the classroom, I would probably do that. I would take a piece of rock salt and I'd hit it with a hammer and you'd see pieces flying all over the place. Okay. It's very brittle. Okay. That's because when you put the stress on it, you're moving the ions out of their best location. You're creating repulsions and they split apart. That might be worth you listening to a couple times over because that's often a test question I ask is about the brittle. Why are ionic compounds brittle? And I think, yeah, that's as far as I was planning on going here today. So if you've done your assignments over the last couple days, you're not going to have a lot more to do. I'm going to be asking you to check your answers to the last couple days and a little fun video to watch. So have a great day. I really hope I have something special for you tomorrow. Okay, I'm going to try. So yeah, stay safe. As always, if you have questions, please contact me. When I host a Google Hangout or a Zoom meeting or something, feel free to pop in, even if it's just to say hi. I'd like to see you guys, see how you're doing. Okay? Take care of yourselves. Stay safe. Let me figure out how to get out of my video. Ooh, hey, I look back to this bigger screen. This is pretty cool. So, yeah, have a great one. Bye-bye.